Welcome back to our series on the FFT. We'll pick up here. So a quick little review. We made a little simulated noisy recording thing here, which plays a bunch of tones and has some noise in it. And then we built a little noise reduction patcher with the PFFT. And then we also rebuilt the classic Forbidden Planet example in Max, which is done here with this FFT equalizer. So if I just turn this on, I'm going to get this noisy recording, and then I can turn up this threshold, and it'll knock out all that broadband noise. So let's just start there. Okay, so that works just the way it did as we finished up last week. If we just quickly review, we have this PFFT object. A PFFT object is a patcher, and the name of the patcher, which is on our hard drive, is called noise reduction. And we told it we want a 512 size FFT. So if I double click this, I can see the patcher. It loads the patcher just like a poly object does. And then inside we have these special FFT in and FFT out objects. We did a little bit of magic in here using this car-to-pull object, which will give us the magnitude and the phase for each of 512 bins or 512 bands in the frequency domain, remembering that we started in the time domain out in our main max patcher. We collected 512 samples in the time domain, and then in here we're in a frequency domain where we take the first set of frequencies and the second set of frequencies and the third set of frequencies, and each sample represents one of those sets of frequencies. So we got away with doing a lot of this and ignoring a lot of details, and that's one of the great things about the PFFT object, is it provides a lot of intelligent defaults for us so that you can just work and not get too tripped up with what can be a cumbersome amount of knowledge that you need. As an example, we came here and we can see that there are a bunch of arguments. We did give it a subpatcher name, we did give it an FFT size, but we didn't give it an overlap factor, a start onset, or a full spectrum flag. So to become a savvy user of these objects, we'll need to understand what those things mean. Another area that we didn't talk about, if we look in the FFT patcher, we go ahead and unlock it, there are some additional arguments for the FFT in, which include the window function, or here it calls the window envelope function. Well, it says it's required, it isn't actually required. There's a little typo right there. If we look at the help patcher, we can see the help patcher properly describes it as being optional. And not only is it optional, but if it's not specified, it uses a Hanning window, which is the default, which is pretty fabulous because a Hanning window is what you'll want most of the time anyway. So to understand all of this, I'm going to go ahead and push some stuff around here in our patcher to make some room where we can work and talk about what some of these options mean. As we described before, we do an FFT. It comes in here in the FFT in. That converts us into the frequency domain from the time domain. We use the 512 samples in the frequency domain. It gets converted back to the time domain, and then it pops back out of this outlet here. So that way we described it, where it would take a block of 512 samples, and then it would go and do the next block of 512 samples, and then go and do the next block of 512 samples. That can be done, but that's not typically what's done, and that's not actually what's happening in here right now, because we've accepted the defaults. So to draw a little diagram of that description, I can use panels, and each one of these panels will represent a block of 512 samples. So if we took a block of 512 samples, and then we had another block of 512 samples, and then we process the next block of 512 samples, and so on and so forth, we would have something that looks approximately like that. The problem is that the basic math of the Fourier transform is based on this concept where you would have infinity. It's really an algorithm from the analog world. And we don't have infinity in a computer or in any sort of discrete or digital system. So as a result, when we chop off the ends of this and we say we just have 512 samples and then there's nothing before it and nothing after it, we introduce a fair amount of noise into the system. So one way we can reduce that noise is we can taper this. Instead of being just this big rectangular block, we could taper it, and we could imagine that it fades in at the beginning of the block and fades out at the end of the block. Well, if it fades in at the beginning and fades out at the end, then we're going to need another set of blocks that are offset, that are also fading in and out. This is called an overlap add technique, where we overlap a whole bunch of these windows. We call these windows, and we add them together, and then we give them each a certain window shape. So that Hamming shape, as an example, has kind of like a nice little curve to it. One place where we can see that is if we use a buffer object. I'll go ahead and make a buffer object, and I'll go ahead and I'll say that it's going to be size in SAMPS 512. If we open this up, we can look at this right here. Buffer messages. There's a message to the buffer called fill, and there's another message called apply. So what we can do is we can fill the buffer with a value of 1. If we do that and look at it, we can see it, sure enough, it's filled with 1. This is what would be called a rectangular window if we were going to do this overlap add. After we fill it with 1, we can apply a Hamming window to it. Okay, and if we look at it, applied the Hamming window, and we can see that this is a nice little bell-shaped curve. So if we wanted to see what these looked like up here, actually we could use a waveform object instead of a panel object and say message set. This buffer needs a name. We'll call it our window. We'll call it FFT window, just to keep it straight. Okay, squish it down like that. Come up here, copy this guy, come up here and say edit, paste, replace, boom. So now we can visualize. We have these two streams of numbers that are coming from the FFT, and this one's fading in and this one's fading out as this one's fading in, and these all get summed together. So it's overlapped, first it's windowed, then it's overlapped and added together. So if we were going to do this process here in the PFFT, we would say that we want an overlap factor of 2. This 2 means that we're going to have 2 overlaps. We could go further. For example, we could come over here to this PFFT patch and we could say 4, and if we do 4 overlap adds, then you'd imagine we would duplicate this further. So with an overlap factor of 4, we're going to split the processing. Instead of splitting the processing into 2, we split the processing of each 512 samples into 4 different layers. PFFT automatically handles all of the complexity of all this overlapping and adding and we just get the output from this FFT in one. It's already been windowed. Remember, it's been windowed according to that default window that was provided. And it's also been overlapped and added for us. So that's pretty convenient. And this is what's going on inside. There is a discussion in the PFFT help patcher under this technical details. I'll leave this to you as a little reading assignment where you can read a little bit about using 2 overlaps versus 4 overlaps, and it talks a little bit about the windowing as well. So you can chase that down if you wish. We're just going to jump straight into some patching here, where we'll repatch these, but instead of using PFFT, which hides all of the details of this windowing and the overlap add, we'll actually get a chance to patch it ourselves. Let's go ahead here, and I'll scoot this guy out of the way. Scoot this one back up here. So we're going to type FFT. This is going to be Max's direct FFT object that doesn't do all the fancy stuff in PFFT. Then we tell it the size of our FFT, which we're using 512. We'll just keep it the same so that it's a little easier to keep track of. We actually have to type in the size of it twice here. And then we have the phase. And the phase we can just leave off, or we can say specifically that it's 0. The reason the phase will matter is because if we do an overlap add with 2, then we would tell it we're going to have the phase of this one be shifted by 256 samples. If we were to do 4 overlap adds, then we would need 4 FFT objects, and then these would each be shifted by 1/4 of the total FFT size. We're going to stick with 2 for now. And I think what's actually going to be best is if we put these into a patcher, a sub-patcher. So I'll encapsulate this for now. And this is going to be FFT noise reduction. Okay. And we can come in here, we'll make an inlet, make an outlet, and then we had another inlet here that was for our threshold. This is our audio inlet. At the bottom of this entire ordeal, we're going to have an IFFT. An IFFT is the inverse Fourier transform, and that will mirror what we have at the top. So let's copy and paste our little patch here from inside our PFFT, which looks like this. Our noise reduction algorithm. So because we're doing 2 FFTs here, we're going to have 2 copies of our patch that are running in parallel. You can kind of think of doing the PFFT with all of the different overlap add streams being different voices, if you were thinking of it in terms of poly. So when you have 2 overlap adds in your PFFT, you're actually creating 2 copies of your patch. If you have 4, you're creating 4 copies of your patch. The output of this FFT object is just like it is for the FFTN, so there's an imaginary and a real output. We connect those to the car-to-pull object just like we did before, and then we can get the magnitude and we can get the phase. So we'll go ahead and do that for these. We'll go ahead and hook up our threshold. And then we need to perform this multiplication as we did in our patch in the previous session. And then we can go ahead and hook up the real and imaginary outputs to our two IFFTs like that. So basically we have two copies of what we did last time. The overlap adding part of this and the windowing part of this is going to happen before the FFT, so this was actually misleading for me to connect those, and after the IFFT. So we'll go ahead and scoot all this stuff down here. There are several ways we can try to implement this overlap add business. We know how many samples we have. So a really simple way we can do this is we can use a count object. The count object, if you aren't familiar with it, you turn it on, it just keeps on counting. So we can tell it to start at 0 and go to whatever we want and have it automatically turn on. So I'll go ahead and do that. We're going to say it's going to count 0 for the minimum count, the maximum count. If we're counting 512 samples, it'd be 0 to 511. We're going to turn it on by default, and then we're going to also have it automatically reset. So this will just keep on looping. Then we can use an index object, and the name of our buffer with our handing window in it is called FFT window. So I can simply do that, and then we should have, if I go ahead, I can just hook up a quick little scope here. And if we turn on the DSP, I'm going to disconnect this over here, come over here. And if we go ahead and turn on the DSP, then we'll go ahead and we can see that something approximating our shape is happening in this window. So we're going to take this window, we're going to multiply this window by our audio input so that our audio input is faded in and faded out at the beginning and end of each frame of this FFT. What we'll then do is we can delay by 256 samples. Trying to remember if the delay object works in samples or if it works in milliseconds here. Yep. So we delay by 256 samples to another index object, which will provide our second FFT window, which is offset by half of the size. And then we can window this signal, and it will now be fading in and out exactly the opposite times this one is. We then do the same thing at the output. So we've applied our windowing to the input, split it up between the two FFTs, then we're going to combine the two IFFTs together after we once again window them. So I'll just go ahead and copy these here, and then we'll take the same window functions, apply them there, and then we'll add them together. We could just combine them at the inlet, but to be explicit about it, you could go ahead and use a plus object. Okay? So that's it. Let's give it a try. Go over here, PFFT noise reduction. We'll hook up our number box, hook up our noisy recording input, and hook up our outputs and see if it works. Okay, so sure enough, it does work. And now we can tidy up this patch a little bit. Okay, so we're going to use some panels to tidy this thing up now. Go ahead and so here we have our 2 copies of the algorithm we're using. Here we have 2 inverse FFTs offset by half the size. And here we combine them. We could say by fading between them, which is essentially what's happening when we apply that windowing function. Okay. That's what this is doing. Scoot all of this down. Then up here we have 2 FFTs offset by half the size. Kind of move this stuff out of the way as best we can. And we're going to use our windowing functions. We're going to split the input between the 2 using the window function. It's sort of like an automated panner, if you want to think about it that way. So at this point, I think you should take a moment to congratulate yourself. What we just did was a pretty advanced bit of max patching. We can now manually create an FFT with the windowing. And even if we weren't going to do this manually, we now have a much better understanding of what's happening in the PFFT itself, so that if we wanted to control these parameters and do these overlap adds, we actually know what's happening. We've actually been through the process of building out what happens. If we wanted to now take our knowledge of this and apply it to this PFFT equalizer, we also would know what to do now. We can copy and paste this patch. We can hook it up. And then we know that in here in our PFFT, this is what we were doing. So if I copy this patcher and then come in here, I know that this algorithm section is where that happens. So I would just paste this in here like so. And we can hook this up like this and this. We can do the same thing with this one. Leave all of our windowing stuff right in place the way that it was. Close this down. We need to be able to write into that EQ buffer, which we did here. And we set these samples in it to apply the EQ. And we get the sound. Now one thing I noticed is there's a little bit of crackling. And I noticed this in the previous example too. So where is that crackling coming from? Probably we've done something wrong. So let's debug it together. because this is the kind of mistake that everybody makes when they start patching these things. So where could that extra little fuzz or crackle or distortion be coming from? It's probably coming somewhere here from these windows. If we were to choose a window, let's say we chose a Blackman window, for example, it's going to have a little more attenuation here at the beginning and the end. Maybe that noise will go away. Except that the noise is coming and going. And so why is that noise coming and going? Probably something is going in and out of phase. So it might be that our count here is a little off, or something about this is not quite right. So what it might be is I might have this count object wrong. You can come take a look at this again. This says minimum count and maximum count, and I read it real quick, and I just set the things to the minimum count and the maximum count. But in fact, I think this is maybe not correct. I believe what it's actually going to be doing is that this is the number of values instead of the maximum count. So let's give it a shot. We'll just see if it works real quick. Yeah, so that fixes the problem. No more crackles. So I'll go ahead and fix this other one as well. We really want to count 512 samples, but still starting at 0. And that'll fix the crackles in this other algorithm as well. So there we go. We've got it cleaned up. We've got a couple of patches now done using PFFT, and now done the manual way. And next time we can jump back in here with the FFTs and talk about how we visualize the FFT. So until then, happy patching.